Now let us start solving problems based on principle of conservation of linear momentum and collision theory. A moving particle of mass m makes a head-on elastic collision with a particle of mass 2m which is initially at rest. Show that the colliding particle loses 8/9 of its energy after collision. Apply principle of conservation of linear momentum. We can write momentum before collision equal to momentum after collision. Let velocities after collision are v1 and v2 respectively. So we can write mu equal to mv1 plus 2mv2. Since collision is elastic, so according to principle of conservation of mechanism, we can write kinetic energy before collision equal to kinetic energy after collision. So half mu square equal to half m v1 square plus half 2m v2 square. That gives us u plus v1 equal to v2 when we solve two equations. Now substitute the value of v2 in equation 1. We get v1 equal to minus u by 3. So kinetic energy of the first particle after collision equal to half m v1 square equal to half m u by 3 square. That is equal to 1 by 9 initial kinetic energy. So kinetic energy final divided by kinetic energy initial equal to 1 by 9. So 1 minus k final upon k initial equal to 1 minus 1 upon 9, that is equal to 8 upon 9. So the particle having mass m loses 8 upon 9 part of its energy. Let us start one more illustration. Two bodies A and B of masses m and 2m respectively are placed on a smooth floor as shown in figure. Two bodies A and B of masses m and 2m respectively are placed on a smooth floor. They are connected by a spring. A third body C of mass m moves with velocity v0 along the line joining A and B and collides elastically with A. At a certain instant of time t0 after collision, it is found that the instantaneous velocities of A and B are same. Further, at this instant, the compression of the spring is x0. Determine A, the common velocity of A and B at time t0, and B, the spring constant. Since initially there will be collision between C and A, which is elastic in nature. So, from principle of conservation of linear momentum, we get mv0 equal to mva plus mvc. That gives us v0 equal to va plus vc. Since collision is elastic, so mechanical energy remains conserved. So we can write one more equation. Half mv0 square equal to half mva square plus half mvc square. That gives us v0 square equal to va square plus vc square. Subtracting equation 2 from equation 1, we get 2va vc equal to 0. That gives us either va equal to 0 or vc equal to 0. But va equal to 0 is not possible. So vc equal to 0. Because if Va equal to 0, then there will be no interaction between A and B, and there will be no compression of spring. So Vc equal to 0. Now apply principle of conservation of linear momentum between A and B. We can write mv naught equal to m plus 2m into v, because velocity of A after collision is v naught. That can be calculated from equation 1, because v naught equal to va plus vc. When vc equal to 0, va equal to v naught. So we get from momentum conservation between A and B, mv naught equal to m plus 2m into common velocity v. So v equal to v naught upon 3. Now from principle of conservation of energy, we can write half m v naught square equal to half m plus 2m v square plus half kx square. That gives us k equal to 2m v naught square upon 3 x naught square. That is spring constant of the spring.